All right, since people are naturally quieting down, let's get started. So our first speaker today is ZuHone. He's an astrophysicist here at CSA, where he works with the ASIS operations team. John got his bachelor's at the University of Illinois at Urbana-Champaign. He then got his PhD at the University of Chicago while working with John Williams. And then he was a postdoc at MIT, Goddard, and the CSA before starting his current position here. His research interests are in galaxy clusters and the physics of the intercluster medium. And he makes lots of wonderful simulations, some of which you may have seen featured in some previous high energy seminars. Today, he's going to be telling us about merging clusters of galaxies with self-interacting dark matter, effects on the X-ray emitting plasma.
Thanks. So, for those of you that know me, you're probably wondering if I'm sick of looking at spirals, and the answer is yes, I am. But I keep finding stuff to do with them. But eventually, I think very soon, I will stop looking at them. So, this is also a sort of a fanciful idea. This was sort of a scratching an itch, sort of what if the dark matter is, as suggested by some theorist, actually is at least a bit collisional, not like super collisional like the gas in galaxy clusters is, but what if the dark matter is a bit collisional? And so while people who were looking at this in simulations were doing things like galaxy formation and other things like that, I said, well, what happens to the ICM? Because very few people were asking those kinds of questions. And so today I'm going to show you the first few simulation investigations that I've done in merging clusters of galaxies with self-interacting dark matter, focusing on the effects of the X-ray emitting plasma. This is work that I've done with Jesus Zavala at the University of Iceland and Mark Vogelsberger, who's down the street in MIT. So we say self-interacting dark matter. What do we mean? Well, basically, the standard assumption is that the dark matter particles don't collide. They only interact with each other and baryons via gravity. But the idea here is that occasionally dark matter particles will collide. And this idea is not just come up with arbitrarily. It's invoked to solve certain problems in galaxy formation. So the first is and a number of you might be familiar with these. The first is the too big to fail problem. The most luminous halos and subhalos in the Milky Way are subdense compared with CDM predictions, so from simulations where the dark matter is just treated collisionously. The core cusp problem, so in the standard CDM model, it's basically NFW all the way down, from clusters all the way down to small galaxies. You have NFW profile-like halos, but many halos at the galaxy scale are flatter. They have cores instead of cusps in the center. And the diversity problem is that there's just a wider scatter in halo profile properties at galaxy scales than predicted by CDM. Now, of course, and there have been a lot of papers about this recently, we could potentially solve these problems with just plain old baryonic physics, saying that the baryons are also gravitating and they're going to, when the baryons are moved around a lot, they're going to drag, to a certain extent, the dark matter out along as well. And so you might be able to solve these problems with baryonic physics. But the jury's still out, and it's more fun to talk about speculative particle physics, right? So these problems may also indicate that the dark matter is not collisionless. So this is not a new idea. It's been looked at for a very long time. So and a lot of people have used observations to try to constrain dark matter self-interactions. It can't be, strongly self-interacting. Otherwise, you wouldn't get the separation, as you see here, between the X-ray emitting gas in the bullet cluster. You see the bullet from the bullet cluster as shown in this Chandra image from Randall et al. 2008. And then the dark matter centroid and the galaxy centroids are mostly, but not completely overlapping over here. And so the dark matter can't be as collisional as the ICM is, but a number of measurements have indicated that have placed upper limits on the self-interaction cross-section of dark matter, like strong lensing measurements. Self-interactions will tend to flatten cores and make halos rounder. The abundances of massive subhalos, so if you have a strong interaction cross-section, then subhalos will get evaporated as they buzz around through their parent halo and essentially, get eaten away by interactions with the particles of the parent halo. and separations between galaxy components and dark matter in plane of sky mergers like the bullet cluster. So there's not much of a separation, but the limits placed on self-interacting dark matter, and the sort of the thing you want to look at here is the cross-section divided by the mass of the as of yet unknown dark matter particles. So this sigma over m is the number you're going to be seeing a lot. So roughly the limits placed by all these things at cluster scales is roughly less, around 1 centimeter square per gram. So this is the number, and there's a nice, very long, very thorough review by Tulin and Yu from this last year, which basically talks about this problem in detail, the constraints, and sort of future prospects. But the question I want to ask is not what's going on between the dark matter and the galaxies, but what's going on in terms of the dark matter and the ICM, because even though we're not talking about interactions, direct interactions between dark matter particles and ICM particles, but if the dark matter particles interact with each other and they change the potential, the ICM, of course, is going to feel those changes in the potential. And so we're answering these questions using simulations. The simulation code I've used for this investigation is a repo. Mainly because it already had all the physics I needed built into it. So I just asked Mark Vogelsberger if it was okay to use it. And then, of course, he told me to ask Volker Springel. And after asking all the correct people, I got all the okays. But basically, the simulation setup is that we've got a large galaxy cluster that we start off with dark matter in an NFW type profile. We put in some hot X-ray emitting plasma, the intercluster medium. This is going to be a relaxed cool core cluster, so the temperature will decrease down into the center. And then because at the centers of relaxed clusters, the gravitational potential is actually dominated by the stars, I'm going to put in a stellar component for the brightest cluster galaxy. So these are three separate dynamical components in the simulation. And then what we're doing, at least for this first set of simulations, is that we're going to take a dark matter only subcluster, and we're basically going to toss it into the center, so that we're just gently perturbing the center. And why are we doing that? Well, so first, I think I got my slides out of order, so I apologize. But want to spend just a moment describing the algorithm for how we implement the dark matter self-interactions, because the way that dark matter normally works in simulations is that you compute the large-scale gravitational potential everywhere in the simulations from both the baryons and the dark matter and the stars, and then you map the accelerations back onto all the mass elements. Here, what we do in a repo is that you have a dark matter particle, say this red thing over here, and it's allowed to scatter with nearby dark matter particles within a simulation time step with a scattering probability. So this is a stochastic approach, basically, given by the scattering cross-section, the sigma over m, multiplied by the mass of the particle in the simulation, times the velocity difference between the two particles, nearby particles, times the time step. So basically what we do is that we draw some random numbers, and if we basically get a hit, if we determine that there will be a collision, what happens is that these two particles collide with each other, they scatter off each other elastically so that the total velocity at the end is total kinetic energy at the end is the same, but the momenta get completely reoriented, so you basically scatter them with an isotropically random angle. For simplicity in these simulations, we assume that the self-interaction cross-section is constant and we vary it in different runs. There are a lot more ways that you can change this. You can make inelastic collisions. You can make anisotropic scattering. The model that we're choosing here is sort of the simplest one because this is the first time we're trying it. We want to be able to easily interpret what's happening. So let's just look at what happens to a single dark matter halo. Set in isolation, it's relaxed. So what you're seeing on the left is the dark matter density profile. What you're seeing on the right is the velocity dispersion profile in kilometers per second of the dark matter particles. And this is a very high, I should say, observationally rolled out cross-section for the dark matter that I'm going to show here in this movie. But the idea here is to show you, at least qualitatively, what happens to an NFW halo when you turn on self-interactions. and for it to happen quickly. So I set this number rather big. So basically, you have the density of the dark matter particles very highest in the center, and so you expect the highest number of collisions to happen towards the center. And so what happens is that the dark matter profile quickly flattens out. So you get this, flat core instead of the cusp that you had in dark matter, and then the profile for the velocity dispersion also flattens out and goes up. And so basically what you can think of is that the collisions between the dark matter particles, let me just run that again very quickly. The collisions between the dark matter, well, why doesn't that work? I'm going backwards. Okay, I'm just going to use the old-fashioned way, sorry. Collisions between the particles on the inner part with particles that are slightly outer that have a higher temperature or like higher velocity, basically means that if you think of the velocity dispersion as a temperature profile, which is more realistic once you have collisions, less so when the dark matter is collisionless, you can think of this as essentially a thermal conduction, which flattens out the density profile, basically puffs up the dark matter, and then and you get sort of a flat temperature profile in the velocity dispersion. This is what happens to an isolated cluster. Now we're asking the question, what would happen to an isolated cluster if you were to actually add some gas in? And so this top left panel shows the dark matter density, which I already showed you. So the dark matter density starts off rather cuspy and flattens out. The top middle is the electron density of the ICM. This one is the temperature of the ICM. And then right here, over on the bottom left, is the ICM entropy. So what's happening is that because this is a very slow, gradual process of flattening out the gravitational potential, that the gas sort of feels this as sort of an adiabatic process. And so the gas is adiabatically expanding. So as you can see, it gets less dense in the center, and it also cools as well. Okay, and if you move, this is 1 gigayear into the simulation. If you move 2 gigayears, this process continues. Now you can see that in this purple curve here up on the right, where the temperature is actually gone up, and that's because, as you can see over here on the upper left, that the density is actually higher here now in this purple curve, where you have the extreme value of the collision cross section. And so because the dark matter density is higher, you actually are now undergoing some adiabatic compression.
Is there any difference between the initial and the zero cross section?
Okay, so that's a good question. So the reason why there is difference, you can get some flattening in the center is that when you get into like this inner region, less than 10 kiloparsec, you're starting to reach the place where noise from like the Poisson noise of the particle simulation, as well as like the force resolution, starts to have an effect. So it is a numerical effect in the center, but you notice that all of this is fairly adiabatic because in all the simulations, the entropy profile is essentially the same, even after 5 gigayears. So you've changed a little bit the density and the temperature profiles of the cool core cluster, but it's still a cool core cluster. The density goes up high in the center, and you have a temperature decrease towards the bottom. So, but what we want to do is we want to mess this up. So what we're going to do is that we're going to toss in a subcluster, and we're going to stir things up a bit. And the diagnostic we're going to be looking at is one that was first discovered with Chandra, known as cold fronts. I'm guessing many of you are familiar with what these are, but in case you're not, these are sharp density and temperature jumps that are on the width of the jump is on the order of kiloparsec, or less than the particle mean free path. This is something that you really needed the excellent spatial resolution of Chandra in order to see. So you have these spiral-shaped edges. If I had a really long pointer, I would show you where the edges are in this image of Abel 2142. And basically, when they were first seen, it was like, oh, look, there's a sharp density discontinuity. It must be a shock front. But it turns out that when you draw profiles across these edges, as you see here, this is a surface brightness profile. So you can see the edge discontinuity in the surface brightness. And you see an edge discontinuity in surface brightness that effectively gives you a density jump. But then these are the spectroscopically measured temperatures across the same fronts. And instead of going from a hotter temperature on the denser side to a lower temperature on the less dense side, which is what you would expect for a shock front. It's the opposite. You go from colder, denser to less dense, hotter. So these are actually contact discontinuities because the pressure is mostly continuous. These are thought to be caused, and you'll see a movie of how this happens, by subsonic gas motions triggered by interactions with subclusters, and many clusters have these. So I'm just going to show a movie. This is a slice through temperature in the simulation, where we are looking at the center of the cluster. See, the temperature goes down. The X marks the position of the BCG. The contours mark the dark matter, and so this is like just a plain old vanilla collisionless dark matter simulation. So what happens is that we have a dark matter subcluster which comes in, perturbs the center, gravitationally tugs at both the gas and the dark matter in the center, but the gas feels the ram pressure from the gas surrounding it, and so it's actually pushed out of the center. It's kind of hard to see that pushing because we're following the potential minimum in that frame of reference, but it pushes it out and the gas sloshes around in the bottom of the potential wheel, kind of like wine sloshes around in gas and forms these spiral cold fronts. You can see that because there's a shear velocity across this edge here, that they form Kelvin-Helmholtz instabilities, which I'll mention again here in a few minutes. So what happens if you run that same movie 3 more times? So the top left is the same one I just showed you, but instead you increase the dark matter cross-section. So my first thought was, well, you'll see less of this sloshing around, because if you give the dark matter a cross-section, make it more collisional, then maybe it's going to feel its own quote-unquote ram pressure, and so maybe you won't separate the two components as much. But what actually happens is this. And I know you're going to have to look at 4 different ones, but maybe you can look at the top left and the bottom right just to see the extreme differences here. So what you're seeing here is that the same process occurs in all 4 of these, but in fact it's actually more violent in a sense. You get these big swings of the cold low entropy gas as you turn up the dark matter cross-section. Now, at late times, everything kind of starts to look fairly similar, but in the middle, which I'll run again just very quickly, in the middle what happens is, so I'll just point it out right about now, is where things are different. The gas is actually a fair bit colder and remains cold for a longer period of time when you have a significant cross-section than when you don't. So I thought, that's interesting. What's happening? Well, there are 2 things going on here. The first one is more obvious. The first one is that, remember that the potential has been flattening. And so when the potential flattens, because you've flattened the dark matter core, what ends up happening is that you basically decrease the gravitational acceleration. So when you give the gas in the center a push, it's really easy to push it out. So that's why you get this big swing far out. A lot easier than in the other case, and why it takes a lot longer to like fall back into the center. But the other interesting thing is that the whole time that the subcluster it's falling in, it's basically falling in, and then all of its particles are coming head on with the dark matter particles in the main cluster. And so what's happening to it is that it's actually getting eaten away, basically, to a certain extent. And so what happens is that as it gets eaten away, it has less of an effect on the stuff in the center. And so you have this weird combination of it's easy to push things out, but then you push things out more gently. And so they kind of like, I don't want to say they cancel each other out, but the effects do kind of cancel each other out, so you get the same effect. But the interesting thing is that because you push things out more gently with a lower velocity, the velocity is lower, and when the velocity, a shear velocity is lower, it means that you've delayed the onset of the Kelvin-Helmholtz instability. So you can see that the fronts in the upper left case are rather boxy because you've got Kelvin-Helmholtz instabilities developing along these. And then along the, as you turn up the cross-section, you've got smoother fronts or colder because you haven't mixed hot and cold phases because of those instabilities sort of ripping up the front surface. It's a very counterintuitive thing I didn't expect, because most people explain smoothness of cold fronts using viscosity and magnetic fields and things like that. I'm not saying we shouldn't do that, but I didn't expect to get less Kelvin-Helmholtz instabilities from making dark matter particles collide with each other. So just to illustrate again the two effects, the main cluster core softens. So before core passage, you've already softened the core. So the red curve is the case where you have a interaction cross-section of 3, and the blue curve is 0. So you can see that in 0, everything is the same after the core passage, where you haven't really affected the main cluster too much. And you do, the collisions with the particles in the subcluster do soften the core further a bit, but not very much. You still have a flat core. But as you can see, that the subcluster is more strongly affected. So on the left, you have a case where the self-interactions were switched on during the merger, and and so what you see is that you had a cuspy dark matter profile here. This is a projected map of the dark matter density. And so on the left, you see it's just kind of like a fuzzy, mild halo enhancement thing. And then on the right, what you see is a simulation we ran where we don't have self-interactions during the simulation, but we switched them on beforehand so that we could actually let both of these halos develop cores. And so in the case of this on the left versus NFW, which I'm not showing here, this would actually even be more peaky. So the effect of the self-interaction sort of, eating away at the subcluster is a pretty significant effect that reduces the effect that it can have on the center. And we have shown, I'm not showing it here, but you can actually see in the paper, that if you just take the two dark matter cores and you flatten them, and then you run the same simulation, you will still get sort of the same violent Kelvin-Helmholtz instabilities and gas mixing as you would in the simulation where there are two NFW profiles. What you actually need is, it turns out you actually need the self-interactions during the merger to eat up the subcluster even further to prevent it from perturbing the center as much. And then this is just showing, if we focus on the era basically after the core passes, which is marked by a dashed line, up to about 2 gigayears, you can see that as you switch on cross sections, that the gas can move out to higher radii in the initial stages by initial up to about 2 gigayears. But that the velocity is in this particular in this early time is lower. So the low or no cross section is these blue and orange curves, and the velocity shoots up fairly quickly. But it takes as you turn up the cross section, it takes a bit longer for the velocity to increase. So during that time, the onset of the Kelvin-Helmholtz instability is being delayed. Whereas, as you can see at later times, everything sorts to start to even out as the cold fronts move outward past the region where the self-interactions are important, which is why everything starts to become more similar. The last thing I want to mention, there's actually a second part to this talk, but I horribly underestimated how much time it would take me, so I'm just going to close with this, which is the last part of this paper, is that an interesting side effect of this is that clusters also can be seen in the Sinayev-Zeldovich effect, and that what you see is that as you increase the self-interaction cross-section of the dark matter and that you're pushing that low entropy Gauss out further, that the separation between the X-ray peak, which is basically like density squared, and the thermal SZ peak, which is like pressure squared, so the X-ray is seen here in the color map and the SZ is seen in the contours, is that the separation between these peaks increases. So you actually get, for at least a gigayear or two, you actually get a period of time where the X-ray peak is actually fairly separated by, like a few tens of kiloparsecs away from the Sinayev-Zeldovich peak. And so if you had a lot of clusters and you looked at this, you might actually be able to provide an additional constraint on the self-interaction cross-section. So there were other things here that I won't have time to talk about, so I'm going to go straight to the... you can see a movie of some other stuff we're doing with a head-on collision, where we're going to be looking at the effects of self-interactions on cluster observables like LX and TX and see what they look like during the course of the merger. But we don't have time to talk about that, so I'm just going to put the summary, and you'll have to look at the top part, the formation of cold fronts part. So, so qualitatively, things look very similar. You still get sloshing cold fronts, but there are some subtle features. You soften the interpotential, you enable larger amplitude gas sloshing, but you're also, really, destroy a huge part of that subcluster, and so you don't accelerate the core as much, but the two effects sort of nicely combine to get you nice, smooth cold fronts, which ironically is what we see in Chandra observations. I'm not saying this is the explanation, but I find it kind of funny. And so you might be able to test this by looking at mini clusters and looking at measuring separations between X-ray emissivity and Tsunai's Zeldovich peaks. Thanks.
Questions for John? Up there.
John? So I think in quantum mechanics, you generally expect that the cross-section depends on the velocity.
That's right, yes.
And you don't include it.
So we're not including that explicitly. It's so in most of these most of these galaxy formation models, what happens is that they have a cross section that does vary with velocity, so that it's small at higher velocity, like at the cluster scale, and that it's higher down at the galaxy scale. It's essentially motivated on the thing you just said. So what we wanted to do here is we wanted to see the effect of a particular value of the cross section, which is why we did a bunch of simulations over a wide range of cross section. But in reality, yes, you would expect that it would vary with velocity.
So what kind of effect? I mean, you can imagine different scalings with velocity depending on exact physics.
Yes, yeah.
Right? And so I guess what kind of effect this would play?
That I'm not sure, except that you might expect. So the issue is that if it's velocity dependent and if the velocity dispersion is lower in the center of the cluster, then you might expect the cross section to be higher there, and the effects to be they're already stronger there, but you might expect them to be even more strong. So.
Other questions?
Observationally, when we get Athena and links and stuff, will this be observable in the velocity structure, do you think? To be able to distinguish between?
Yes. So,
I mean, at least sort of in your up to 2 gigayear sort of thing, where you were actually seeing some differences.
Yeah. So I didn't spend a lot of time in this paper looking at the differences in the velocities here, but you would need something like Athena or Lynx to see it, because if you just had, like, say, the 1 arc minute resolution afforded you by Prism, you wouldn't be mapping the velocity, average velocity in that region would probably be very similar between the simulations. So you would need something a bit. The worry I have is that this is one effect in clusters along with a bunch of others, right? Like AGN feedback, magnetic fields, viscosity, potentially, things like that. So.
Any final question? All right, let's thank John again. Our next speaker is David Principe. He's visiting us from MIT, where he's currently a research scientist. David got his bachelor's at Ohio University and his doctorate at the Rochester Institute of Technology, where he won an award for his dissertation. He was then a postdoc. He won a postdoctoral fellowship that he took to Universidad Diego Portales in Santiago, Chile. And he works on all aspects, all stages of star formation with a very multi-wavelength approach from radio to X-ray. Today, he's going to be telling us about observing crowded fields with Chandra-HETG data, mitigating source confusion in pre-main sequence stellar cluster IC 348.
Thank you for that very nice introduction. I'm assuming the mic works okay, so we'll just stay with that assumption. As was mentioned, my name is Dave Principe. I'm over down the road at MIT. Some of the collaborators that I work with directly on a project that inspired this research I'm going to be presenting today are Dave Hunemerter, Norbert Schultz, and Moritz Gunther. And as was mentioned, I'm part of the Chandra-HETG team. So I'm excited to talk about some of my research today. This observation of the premium sequence stellar cluster IC348 sort of motivated me to understand how observations of HETG, observations of crowded fields, suffer from a lot of complications. And it motivated me to write a routine or create a method to mitigate some of these complications. And I'm going to talk about some of that today in hopes that maybe some of the community would be inspired to use HETG to observe more deeply crowded fields. So the outline of my talk is going to be as follows. I'll start by introducing some of the basics of HETG in case there may be some interested new users in the crowd. Then I'm going to talk about some of the problems we currently face when observing crowded fields with this instrument, and how this is a barrier to pursuing more complicated yet more scientifically rewarding campaigns. I'll present a method I developed that can be used to mitigate some of these complexities so as to encourage more astronomers like you guys to pursue these types of observations. And finally, I'll be talking about some very early science results from the brightest 10 premium sequence stars that spawned this research. So I don't think it's going to take more than one slide to motivate you about why observations with HETG or high spectral resolution observations are important. So shown here on the left and right are X-ray spectra from the exact same source, a classical T-star star T-CHOP, demonstrating the ability of HETG, the high energy transmission grating, to distinguish individual emission lines from the underlying continuum. While the models fit to both of these spectra are the same underlying model, the ability to distinguish these emission features provides a wealth of information essential for constraining stellar properties such as coronal temperatures, densities, and abundances. So before I go into more detail about using this instrument, I wanted to just take a slide to cover some of the basics of how the instrument works. HETG is a transmission grating instrument which uses diffraction as a means to disperse photons from sources, providing spectral resolution much higher than the ACIS-CCD resolution alone can provide. So shown here is the gratings equation, which is responsible, it's my only equation, which is responsible for producing the images below. So this is a HETG observation of Capella. This is taken from the Chandra POG. At the very center, you see the undispersed 0th order point source of Capella. And around the sides, you see the HEG and MEG dispersed spectral components. HETG is made up of HEG and MEG, which essentially are two slightly different gratings with slightly different periods that provide slightly different resolutions. But both of these are used in conjunction to provide high-resolution X-ray spectra of whatever object you want to observe. And so if you look closely at the extracted box in teal there, you can see a nice, beautiful spectrum of this particular star. So at this point, you might be wondering why you haven't used this instrument for your science case. Well, what I've purposely failed to mention so far touches upon the fundamental thing that most of us struggle from. X-ray astronomy tends to be pretty photon-starved. And in the case of gratings, you need a lot of photons to fill up those bins to get a high signal-noise ratio spectra. And unfortunately, most sources, at least in the premium sequence stellar evolution area, they're not quite bright enough for the effective area limitations of Chandra to pursue without a really long, maybe 200-300 kilosecond observation, pointed observation. So shown here is the TGCAT public database of pipeline-reduced Chandra high-resolution spectra. All are the non-proprietary pointed observations of low-mass premium sequence stars observed with the gratings over the 20 years lifetime of Chandra. So a handful of these objects have a couple sources in their field of view, but this represents roughly 20 to 25 of all the premium sequence stars observed by HETG over the 20-year lifetime of Chandra. So it's a great instrument, but unfortunately sources don't tend to be super bright in the premium sequence stellar community, so it's hard to observe lots of sources efficiently. Nonetheless, many of these objects are very interesting, especially to me. One of my side interests is resolving and imaging circumstellar disks around nearby young stars. And so these are three particularly exciting examples of accreting premium sequence stars with beautiful disks shown here in the optical and then the sub-millimeter with ALMA and VLT sphere. So some of these apparent disadvantages, such as photon-starved observations, can be mitigating by exploiting one of Chandra's greatest assets, its high spatial resolution. In other words, if you need a few hundred kiloseconds to get enough photons for one source, you might as well point Chandra at targets with a few other sources in the field of view for a bit longer, maybe a factor of 2 or 3, and get some extra spectra. Shown here are a few examples of crowded fields where long pointed observations have been and can be used to obtain a large number of spectra all at once. So in the upper left, we see IC348, that's the stellar spectra, the stellar cluster that I'm going to be presenting today, observed with HETG. Down here, you see M31, which was observed with HETG, with a bunch of low-mass X-ray binaries apparent. And in the upper right, a distant but massive star-forming region, M17, which is really hard to see on the screen, but there are a bunch of sources there, I promise you, that represents an interesting target that might be able to be pursued if you can take into account all the contamination that you get from these really deep observations with HETG. And one of the spectra from the data sets that I've been analyzing that sort of motivated this research project sort of demonstrates some of the issues that we have. You have the black is the data, the red is a spectral model fit to the data, and we see some features that we don't believe are astrophysical in nature, and we believe are likely some confusion from dispersed spectra in the field. So let's say I'm bored of showing some real science stuff, and instead I wanted to wow you with my animation skills that I've spent years honing in Keynote. Here's an illustration of an HETG dispersed spectra. So we have the 0th order point source undispersed at the very center, and the grating arms dispersed spectra around it, shown as a cross. So let's say I want to extract the spectrum of this object. In general, I would simply take the photons from inside the red box and run them through the various super helpful chow routines, which many people have worked very hard to develop, and the output would be a nice, and hopefully a nice spectrum. Now let's say I want to observe a field with an extra bright source in it that happens to overlay with the spectra that I'm excited about, or I'm interested in extracting. Well, this isn't so bad. It's just one extra source. I can probably be careful about the extraction regions. I could maybe throw out some photons. I could probably get away with doing something like this. But what if we throw in some chicken pox-like scenario where you have a bunch of point sources also in the field? So these are stars or what have you in the same crowded field that aren't bright enough to disperse enough photons to be a problem for their dispersed spectra, but the 0th order photons still arrive at the detector, and occasionally they can intersect with the grating arms themselves, and this gives you a problem because if you're going to extract the grating arms, you're going to get that point source too. And I think you see where I'm going with this. You can add more and more sources to this field, and it becomes overly complex. Well, lucky for us, those who designed Chandra thought of this issue to a certain extent, and so we have something already to help mitigate this process, and what's called ACES order sorting, or the amazingly named plots called banana plots. So essentially what you have here on the y-axis is the ACES energy detected, the energy that as detected from ACES of photons arriving at the detector on the y-axis. And the x-axis is this m times wavelength, or the left side of the gratings equation, which is essentially the geometrically dispersed spectra. And so if you have a nice bright source, you'll be able to get a nice plot like this, and you can extract the correct photons and get your final spectrum. But let's say you have this annoying source in the field of view, and there are some which would provide some additional photons in areas that might intersect your source of interest. And so this would occupy this region in the ACES sorting plot. So let's say these photons are here. So it's a particular energy of photon, according to source number 2, that lands right here. So in this case, you're lucky. These photons didn't intersect with where HETG thinks there should be photons for your source. And so ACES order sorting gets rid of these photons, and it's not a problem at all. But as we move this observation around, depending on where the source is in the particular field, these values can go up and down. And let's say we take a case where maybe we're looking at this arm and this intersection. There are scenarios where you can just unfortunately be unlucky, and the exact right kind of photons can land right where they're expected to land from your source. And in this case, you extract that spectrum, and you get some unfortunate photons there that shouldn't be there. And you need, how do you manage this? So ACES sorting is great for a first order effect, and it's useful for identifying obvious sources of confusion, but it fails in these unlucky scenarios. And so if you just have a couple sources in your field, generally you're fine, you won't have a worry. But if you have 50 to 100 sources in your field, you have to start worrying about this sort of thing. So this was motivation for me to develop a routine to sort of help mitigate these issues. So the purpose is to identify regions in your extracted spectrum with what I'm calling contaminating photons from a different source. So if I say contamination, I don't mean contamination on the ACES CCD. I mean contaminating photons from a different source that ends up in your extracted region. So the input for this routine that I've developed is simply the RA index of the source, sources that are in your field of view, an estimate of their source counts, which you can get from running LabDetect, the event file information, so we need some fit keywords, and some tweakable parameters. And the output is simply a bunch of DS9 region files that show you where the grating arms are in your crowded field. It shows you locations where there's confusion from spectra, and confusion from point sources. And it will also output some ISIS and Sherpa compatible text files that will overplot the areas in your spectrum whenever you're plotting your spectrum where confusion could occur. So it can warn you when you're plotting your fitting spectra where there might be confusion from other sources. And also it allows you to potentially ignore those areas when you're doing your model fitting. So more specifically, for spectral confusion, you simply convert the RA index to detector coordinates. You identify the location of the MEG and HEG grating arms based on the roll angle of the detector. Each HEG and MEG spectra is essentially a line, so you know the equation of that line. And so you can find where these two lines intersect with each other for multiple sources in the field of view. If they intersect, you flag it, you identify the energy where those intersect, and then you put it in a file for later use. And the same sort of thing that happens for point source confusion. So I can talk a little bit about this from a geometry perspective, my killer animation skills again. So here we have a simple HEG and MEG spectra. For each of these lines, you can use the equation of the line, and we know the slope, we know the y position, we know the x position, so we can solve for the intercept. You do this for every source in your field. You have a bunch of sources, so you have a bunch of lines. And what you simply do is you identify for every pair of objects in your field where these two lines intersect with each other. And with a little bit of math, you can work out where this intersection is and how far it is from the 0th order position. And this gives you an idea of the actual energy or wavelength where this contamination occurs. And so it's important to note that this is all based on the geometry of the instrument. So the program doesn't know anything about the source's spectrum. And so it identifies where spectral contamination can occur, but it doesn't necessarily specify where it will occur. If the photons from this source aren't the exact right energy to contaminate this, it will flag it as a possible contamination site, but you won't actually see some confusion or contaminated photons because the ACIS order sorting would have already handled it. So you can do the same thing for point sources. Let's say you have a dispersed spectrum here, and you have a contaminating point source that's sort of close to one of your grating arms. This is a nice case where there's just one point source, but of course in a crowded field you can have hundreds of these. And so you can work out with some simple math, again, the same sort of concept. How far this point source is from your grating arm, and how far it is from the 0th order, and thus the energy where it can contaminate. So to test out this routine, I did several simulations with Marx, a Chandra ray tracing simulator. So effectively, I created 6 sources. Their spectra is based on emission line spectra, thermal spectra. They're very bright. There are 6 individual ones, and I'm simulating them on the ACIS S array. And so what I do is I have 6 individual spectra, so I know each spectra very well. And here's an example of one of them. So this is one of those objects and its spectra that I've simulated after having gone through the HEG instrument. So what I can do is I can take those 6 sources and I can concatenate them onto one observation and create a mock observation of a crowded field. And then I can run my routine on this crowded field. I know what the spectra of these sources should be because I know individually what they're simulated as. And so I can extract them after running them through Marx in this mode to see what their actual spectra look like after they've been in this crowded field. And so I run my detection algorithm on this. And it identifies the sources. This is just an input source list that I provided. It identifies from the FITS headers where the grating arms are for every single source. It identifies where there are point sources that fall onto one of the grating arms of the other sources. So that's where the blue crosses are. And lastly, it identifies regions where 2 spectra intersect with each other, as designated by the pink crosses. You can see this is sort of like the worst case scenario simulation possible. So there's a lot of issues here that you might not see in normal observations. But it's just to demonstrate the power of this sort of technique. So we can take a look at the source A extracted spectrum from this mock observation. So the black spectrum here is the true spectrum of this object without being in a crowded field. And the underlying green spectrum is the spectrum extracted from this mock observation. So just to be clear, there is green everywhere, it's just overplotted. So where you see green and not black, that's where the contamination or the confusion is happening. And so you see from this extracted spectrum in this crowded field, we have a bunch of emission features that shouldn't be there. They're from other sources. But they made it through the extraction process because they fooled ACIS order sorting. And so we need a way to handle this because when we do an actual observation, we're not going to know the true spectrum of every source. And so we want to make sure we can get a handle on that ahead of time. So we're going to take a zoomed in look. So here's source A. This is what we're extracting. This green region here shows you the extraction region. And here are some zoom-ins of the areas of the spectrum that get contaminated. from being in a crowded field. And the blue and red dotted lines are produced by the routine that I wrote automatically, generated based on the geometry of the field. And it correctly identifies the blue being point source contamination and the red being contamination from spectra from other sources. It correctly identifies and flags this area that's saying, hey, there's probably a problem here. You should double check to make sure things are going on the way you expect. We can take a look at another source in the field, source D. So here's the spectrum. In general, that's a pretty nice normal spectrum. The black is the uncontaminated version. The green is the contaminated version. So we see some feature right here. So we're going to zoom into that bad boy. You can see the extraction region again here that's being taken for source D in this case. And what I want to draw your attention to here is this red area right here. And so the program flags it as a source of spectral confusion. And what's happening here is this yellow circle here, the source underneath the circle, its dispersed spectrum is along the line of source D's spectrum, and unfortunately it's the appropriate energy to screw things up and to cause confusion that you otherwise wouldn't have known is there. So the program flags that so that you can go through and model it out if you can. So there are cases in this particular worst case scenario where for source D, if we take a look at another extraction region, there are cases where ACES order sorting does a really good job and there is no confusion. But the program itself identifies areas still where there could be confusion from other sources, but those sources didn't have the appropriate energies at that wavelength to actually cause confusion. So simulated observations are amazing, especially for my case, because I can throw as many photons as I want in them. But unfortunately, I live in the real world where I have more photon-starved observations. And so we can run this on one of the OBS IDs of IC348, which is the stellar cluster that I've been working on, to demonstrate there are some tweakable parameters that you can use. So in this case, let's say, for this routine, it spits out a lot of information, but you can intelligently reduce some of this by adding some extra constraints. So let's say you have a super bright source in your crowded field, and you only care about extracting that really bright source. If it's really bright, you might not care if there's some point sources that fall on the dispersed arm that's only a few counts. And so you can say, well, if there's a source with only a few counts, just ignore it. And so that's one of the tweakable parameters, for example, you can ignore. But running this routine on actual data, so IC348, I've tweaked some of these parameters so that the amount of information is not overly much. So here are the 4 brightest members of this stellar cluster. Here's the program finding where the grating arms are for these brightest members. Here's where the spectra from these particular sources intersect with each other, so where there could be spectral contamination. So the code correctly finds that. And lastly, it identifies some 0th order point sources that also fall within some threshold of the spectral arms. And so all of these objects could cause problems in your spectra if you don't know ahead of time that they're there. So to summarize this tool before talking a little bit about some science results that I have, the purpose of the tool is to identify regions in your extracted spectrum with contaminating photons from a different source. And so like I said, you simply input RA and DEC, an estimate of the source counts, event file information, and some tweakable parameters, and it could help you constrain in your plotted spectrum that you'll eventually fit where there can be contamination from crowded fields. So I wanted to give a few slides, at least, on some of the early results of the science project that sort of motivated this crowded field stuff. And so here is some early science results from a 500 kilosecond observation of IC348 with Chandra-HETG. So on the left is WISE data, mid-infrared, and on the right is Chandra X-ray information. And of course, this is sort of what each source would look like. It's dispersed spectrum. The age of this cluster is about 2 to 3 million years old, and it has 400 cluster members. The age is important because this 2 to 3 million years sort of represents the median lifetime of disks. So this cluster is at the cusp of disk dispersal. Once these disks are dispersed, the planets that are forming in those disks no longer have material to form from, and so the idea is that planet formation at this stage might be halted to a serious extent. Understanding X-ray emission at this stage of stellar evolution is important. These pre-main sequence stars, these low-mass pre-main sequence stars, are magnetically active. And the X-ray emission that they give off is important in understanding mass accretion, a fundamental property of how all low-mass stars gain mass. Coronal abundances, which is important in understanding how you go from initial conditions of molecular cloud material to the final stars. And also disk ionization. Knowing the X-ray spectrum of individual stars that host planet-bearing circumstellar disks knowing their X-ray spectrum could give you a handle on how important ionization is, because the X-rays are capable of penetrating to deep, the midplane levels of the disks where planets are forming. And so understanding and constraining X-ray emission for this stage of stellar evolution is important. So if we zoom in a little bit on the center of this cluster, in one of the HETG observations, we can see about 10 cluster members, 10 of the brightest cluster members of IC348. These are a handful of their names and their spectral type. But because this is a particularly exciting cluster, it's really well studied. And so every member in the literature has spectral types, has ages, has whether or not it's disk bearing, has accretion signatures. And so we can compare some of our X-ray spectra to some of these other scenarios for these young stars and attempt to make some inferences. So one particularly exciting result of these observations is we caught V706, which is a K2 star with no disk. We caught this in a particularly violent outburst or flaring event. So the count rate increased by almost a factor of 20, 21 or so during the observation before it fell back down to near quiescence level. And observing this with Chandra-HETG during the flare provides us an interesting way to understand the evolution of the temperature, the chemical abundance throughout the flaring event. We can bin this in different time periods throughout the different flare moments and understand how the chemistry and how the temperature is evolving over time. And if you want to just take a look, there are some differences in the spectral signatures of quiescence versus flaring event. You see a whole bunch of new iron lines popping up, which is likely a result of the much higher temperatures during the flare. So there's some exciting science that could come out of that as well. Of course, X-ray observations, high spectral resolution X-ray observations of low mass stars is also exciting because you can get a handle on accretion signatures that you otherwise couldn't do with low resolution X-ray spectroscopy. So accreting low mass premium sequence stars exhibit these signatures which help constrain the temperature and density of the accretion shock region. So over here on the left is the, Over here on the left is the HETG observation of TW Hydra, a very nearby, very bright accreting premium sequence source. This is the magnesium-11 triplet area. This is from Nancy Brickhaus's paper in 2010. Some work was also done by my former advisor, Joel Kastner, on TW Hydra back in 2002. So this is like an ideal and amazing spectrum of a very nearby source with a ton of counts. And so you can clearly see the triplet here, the R, I, and F resonance intercombination forbidden emission line. And these ratios can be used to really constrain the accretion shock regions, the temperature and the density, as long as you're using these ratios in conjunction with some other spectral features. So comparing this to our observations, the y-axis is a little bit different. It's not counts, this is count right now. But these are the 7 or 8 brightest sources in IC348. Each color is a different source. So this was just a way to quickly plot this to see sort of how many photons we might see from these events. Overplotted are the three lines, the same 3 lines. I think these are the same scale. And so you can see that for a couple of the brightest sources, we do actually detect the RI and the R, most likely I, and possibly F lines. But we're still working on understanding, well, frankly, we're not sure there's going to be enough counts to do the research that we want to do for this particular science, which is a huge bummer because one of the motivations for observing so many stars is that we were hoping some of them would be accreting and showing the signature. But at this moment, it looks like we might not be able to do that for too many different objects, which is unfortunate. Spectral fitting, a whole bunch of these sources, as I mentioned, can produce coronal abundances, which I've plotted here. So these are coronal abundances compared to the photosphere, solar photospheric abundances. On the x-axis, you have the different elements. So we have neon, magnesium, silicon, sulfur, iron. And some things that pop out to you right away is the IC348 cluster members appear to be pretty iron deficient, pretty magnesium deficient, and have a pretty wide range in neon. Now, of course, this isn't super meaningful without error bars. I recognize this. And so constraining this with error bars is computationally expensive, and we're doing that right now. We're working on this. We've done it already for a couple sources, and the errors aren't huge. But one of the motivations behind this is once we have some decent error bars, what we'd like to do is compare these coronal abundances to various properties of the stars, like the presence of a circumstellar disk. Maybe in stars with mass accretion, where the star is collecting material from the disk and accreting onto the star, you might see some different coronal abundances. But more importantly, we'd like to compare this to other stellar clusters that have been observed with gratings observations. For example, the ONC and the Taurus Auriga region, which was done with XMM. And so once we do that, we'll be able to make some more statements about how the initial conditions, which are presumably different between different clusters based on their paramolecular cloud, might manifest themselves in different coronal abundances. So there's a lot more science to come out of this. Obviously, we're still in the process. But in summary, X-rays play an important role in stellar evolution of low-mass stars, and thus studying them with high-resolution X-ray spectroscopy offers a window into these processes. Given their typical brightness, it makes sense to spend longer amounts of time on clustered regions where the HETG instrument can be used more efficiently. I hope I've created this method that you guys can use as a community to utilize this so that we can observe more complex, more complicated regions, not just in pre-main sequence stellar evolution. You give me a field with any number of objects that's compressed, we can run this code, we can identify where there's spectral confusion. And so hopefully this can be used as motivation to get some deeper Chandra-HETG observations of some crowded regions. Thank you.
Questions for Dave?
Do you want to move, because I've already asked once.
Dave, can you use the zeroth order spectrum to give a probability of where the photons would be contaminating?
Yeah, so the zeroth order spectrum of the contaminating source. Yeah, you can. There's lots of things I haven't done yet. You can also use the dispersed spectrum of the contaminating source to infer the regions that are contaminating the source of your interest and model that out. The first step is sort of to identify where this contamination can occur. And after you do that, this tool provides you with that capability. You can then go through and model how you want to try and remove those photons, or how you want to model those photons when fitting your spectrum. So yeah, you can do that.
Can you improve the decontamination algorithm if you use, let's say, 2 spectra at different rolling angles?
That would be a question for some contamination people in the crowd. You mean the decontamination?
For instance, you have
You mean
2 spectra with 2 position angles of your dispersion relation. So obviously, you should be able, if you process 2 of them simultaneously through the code like yours, you should be able to also remove the effects.
Yeah, so at different roll angles, you'll have different locations where there's confusion. And so if you have this is normal. I mean, some people do this anyways. All these observations are oftentimes broken up into 10 or 15 different observations. And so if you do have a bad case of confusion, you can just throw out that observation. Or you can use an observation where it's not confusion in that region to identify what those photons should be and try to model them out in the area where it is confused at a different roll angle. I mean, that's one of the unfortunate side effects of having really long observations. These things are broken into tons of different OBS-IDs with different roll angles. And so if this was one nice pointed observation, this issue wouldn't be so hard to handle. But we have all these different OBS-IDs, roll angles, and it gets complicated. If you're dealing with 2, 3 spectra, it's not a big deal. But when you start dealing with 50 spectra, you want to automate this process, trust me. And so that's what this is motivated for.
You want to go back and answer?
Rudy's question, basically.
Okay.
That's what the Galaxy Prism did, by the way.
Yeah, that's where the Galaxy Prism did.
Yeah.
That's what I asked.
No question, Greg?
How are you able to discriminate between coronal and photospheric abundances?
It's difficult. But for this feature, essentially you get density, you get a specific density and specific temperature. And so for soft X-ray accretion, for low mass stars based on the mass of the star itself, it's going to be around 3 million Kelvin or 1 million Kelvin. And so if you can identify a plasma that's higher, high density and that specific temperature, you have a good shot at saying it's, from accretion shock.
Final question?
Well, just to ask, what about the LETG? Do any work with that?
No, that's to be determined. So I realize this might be useful for the other gratings instruments. I'm particularly working on the HETG right now, but this would be something I'm definitely looking forward to trying with other instruments as well. They each have their different complications, so it would be a little bit different, but it hopefully is doable. I mean, with those, yeah, well, let's end it.
All right, let's thank Dave and John.